Okay, now that we have added another circuit element, an inductor to the circuit, let's look at some analysis here. So we're starting off with a DC kind of circuit. When we draw a supply or a power supply or a voltage source like this, is a DC circuit. And so we're going to have inductors in the circuit, and we have two resistors in the circuit. And so we're going to start off with just looking at what happens as a function of time in some of these circuits. Okay, so it's asking for the time constant. It's asking for I of t. So in the derivations in the book and in the equations we have here, so these two equations on the top, or actually the three top ones, are related to RL circuits, right? DC. And so, but what they assume is that there's only one L and one R, right? There's only one L and one R in here. Okay. And so in our circuit, we have a couple of each. And so we need to simplify our circuit a little bit. And remember, when we have resistors in series, they just add up. When they're in parallel, we do the 1 over thing. And inductors act just like resistors in terms of how you combine them in series and parallel. So if we have two inductors in series, they just add together. All right. Remember, capacitors, when we get to them, capacitors are the opposite. Capacitors, when they're in parallel, they just add up. And when they're in series, we have to do the 1 over stuff. All right, so let's make this circuit have just one of each. One inductor and one capacitor, or one resistor. One inductor, one resistor. And we can just, I guess we'll just call them L and R to match the equations that we have. They're the total resistance. And so, looking at our circuit, we've got, what is it? Parallel series, what do we have? So, hopefully you can see that everything is in series. There's just one current, and it has to go through everything. There are no branching off, no choices, right? The current has no choices. The charges flowing have no choices. They have to go through everything to flow around in the loop. All right, and so we have everything in series, and so the two inductors are in series with each other, even though there's a resistor in between, but it's all the elements are in series, so the order doesn't matter. So we can say L, which is L total. L total, it's just going to be L1 plus L2 equals 0.3 henries plus 0.2 henries. So L equals 0.5 henries. All right, for the total inductance of our circuit. And then similarly, R is the total or the equivalent resistance. And again, these two resistors are in series with each other. They're in series with everything else, but we can combine them with each other. Changing the order doesn't matter. And so we've got R1 plus R2, which is 5 plus 2 ohms. And so R is 7 ohms. Okay. So we could write a differential equation and solve for this. We could do KVL around, let's just do KVL around the loop just for practice. And so going around the loop, there's only one loop, so we just do KVL around the whole thing, and we would say negative 9 volts, assuming the switch is closed, all right? Negative 9 volts plus, remember for inductors, V is L di dt. All right, so if we want the voltage across this inductor, and remember this is V of an inductor, V of a resistor from Ohm's law way back when, and we still have Ver, V equals IR. Maybe we should make them all the same I since they are. All right, so when we hit an inductor, we're going to do L di dt. When we hit a resistor, we're going to do IR. And so coming around here, we'll assume everything is nice positive sign convention. Okay, and so hit the first inductor, it's going to be L di dt, 0.3 di dt. Hit the first resistor, it's going to be IR. I'm calling my I too many different things. 5I. Hit the second inductor, it's going to be another di dt, so plus 0.2 di dt. and then hit the second resistor is going to be plus 2R, I'm sorry, plus Ri 2I, and we came all the way around back to where we started, we get equals 0. So for the whole circuit, we could have this kind of a differential equation, and as you might guess, people have gone through and solved this differential equation many times. And we would get a similar equation if we're going to do the same current, do the small one, we would just have one L di dt and one Ri, but you can see how adding resistors in series, we could just factor this out, we would get 7I. That's what we had for R was 7, right? R total. Same thing here, if we factor out the di dt, we get the L combo is 0.3 plus 0.2. That's what we had there, right? So you can see that those two circuits have the same differential equation governing them, so they are basically the same circuit, right? Okay, so we aren't going to go through the whole diffie-q stuff, but let's go ahead and solve what it's asking us for here. So the first thing is tau. So tau is what we call a time constant, and it's in the exponential here. So when we have this type of a linear differential equation, constant coefficients, we know that we have an exponential type response, and so we have these two choices for I of t. Which one do we use? And it depends on what the circuit is. So if we see this first one, what's going to happen in this circuit? What happens with inductors? At first, when you close the switch, right, we're going to have current flowing, but it's going to be basically these are coils. Remember, coils don't like change, and so they don't like changing current, so it's going to slowly ramp up the current. It's not going to just jump instantaneously, because if we did jump instantaneously, di dt would be, di was a big change over a small time, di dt gets huge, we get a huge voltage, right? And so we can't get infinite voltage for sure, and so inductors limit the current, so it'll slowly let the current ramp up. And what happens when the current reaches its maximum is that actually then, the current reaches maximum and it peaks out, okay? And so it levels out at a constant value, and then the inductor acts like it has no resistance. So we can kind of think of the inductors as having a variable resistance. At first they're holding back, resisting the current, and at the end they don't resist at all, and it's like they're not even in the circuit anymore, because di dt goes to 0. Right? If the current levels out, there's no change. Di dt goes to 0, so the voltage across the inductor goes to 0, so it's like it's a short circuit. The opposite happens if, say, the switch has been closed for a long time, and down here we're going to short out the source. We're going to take the source out and just close across here so that all the current goes through here and the source isn't in the circuit anymore. We could think of opening the switch on the circuit if that helps, but basically shorting across here will take the source out of the circuit. Then the inductors, again, they don't like the change, and so they will try to hold the current up until they get rid of all the energy that they have stored in them, and then the current goes down. And so this first one, exponentials with a negative in them, start high and go low. So this must be when the switch has been closed for a long time, and then the source goes away. And then this one is a growing exponential, right? And so the second one is for when there is no current, the switch is open, the circuit is open, we close in on the source, and we start getting current to flow, and it grows up. All right, so for this first case, we're talking about the switch getting closed. We're going to use this equation. All right, so I of t is going to be V over R. How does it get to be V over R? If L is 0, or if there's 0 resistance, the voltage across this is 0, then the only thing in the circuit is a resistor, so the current then is just voltage, source voltage divided by resistance. So that's what this maximum current, where the maximum current comes from. The maximum it can be is when the inductor's acting like a 0 resistance, but acting like a short circuit, just like there's just a wire there, and the only thing in there is the R. All right, so that's the maximum, and then we have 1 minus e to the negative t over tau. Yeah, okay, that's not a parenthesis. Negative t over tau. All right, so it's going to be a growing exponential. It's going to go something like that. Right, so the maximum is V over R. This is I of t. This is t. Okay. So first thing you can ask for is tau, which is a good thing. Let's go ahead and calculate tau because it's in the other equation. So tau for an RL circuit, tau is just L over R. Right? Different circuits will have different taus. If there's an RC circuit, it's just tau is RC, vice versa, but we'll go with this one. And so then we have 0.5 henries over 7 ohms. So tau is 0.5 divided by 7. 0.0714. Okay. 74 milliseconds. Yep, because tau is a time constant. Units are seconds. And then it says, what is I of t? So I of t is V over R, where this V is the source voltage. The book might use an E for electromotive force of the source instead of V, but VE, which they're all voltages, they're all potential differences, they're all the same. All right, so our source voltage in this case is 9 volts, and then our resistance, the total resistance we're just going to do like for this circuit is 7 ohms, and then we've got 1 minus e to the negative. It's t over tau, so let's do 1 over tau. 1 divided by 0.0714. 29, keep a few extra sigfigs, why not? Okay, 14. Pretty much 14. T. Okay. So, and this is in amps, if everything else is in the right units, which looks like it is. And so 9 divided by 7, I guess we can do that in a minute. Maybe. So I of t for part A, I of t is 1.29 e to the negative 14 t amps. Okay. So if we wanted to know when the current got to 1 amp, for example, or what have you, we could just put 1 for I of t equals 1.29 e to the negative 14 t. Divide through, take natural log, solve for t, right? So we can find either, if we're given a time, we can find a current, or if we're given a certain current, we can find what time that happens, how, when does it get to a certain level, what have you. Okay, what is the maximum potential energy in this inductor? Okay, so max potential energy in the inductor. So when is that going to happen? What time value is that going to happen? Well, is it going to be, well, first off, let's look at the potential energy equation. So potential energy for an inductor, 1/2 Li squared. Little I, big I, it doesn't matter. All right, and so for this inductor, it has the same current. This current is the same current, right? There's only one loop if we equivalence to non-equivalence. And so, but in this case, we want L1 for this inductor only, because we're talking about now going to we have to go to the full circuit because the 0.3 Henry inductor is not really seen in here. It's inside of that one. So we have to break back out and go to the big circuit. So PE1 or something. All right, so like I said, when does the maximum happen? It happens when the maximum of this current happens, which is out here, right? So the maximum current is this limiting asymptote value here, which is V over R, right? So I max 1/2 0.3 henries times I max, which is 1/2 of 0.3 henries times the maximum current we just found here is the 1.29, right? So 0.5 times 0.3 times 1.29. 0.323. So PE1, I guess, 0.323. So everything is in the correct units, henries, amps. Whoops, I forgot to square though. 1/2 Li squared. take this times another 1.29, 0.416. Don't forget the square. Right there. 0.416. All right, like I say, everything is in the correct unit. So what's the correct units for energy? Joules. Okay. Oh, we're running out of room, but let's see if we can make it. So B, short the source, and now what's the current? Okay, so that's what I was talking about. We're going to take the source out of the circuit, put a short circuit across it, and so basically it's gone. All the current from it will go through here. It will not choose to go through any of those. The switch is still closed. And so now we've just got a loop, and all that's got in it is passive elements. And so if the source hadn't been in there, so we're going to assume it's been closed for a long time. So we reach this maximum current, and then we suddenly get the source out. If the source hadn't been in there for a long time, there would be no current. Nothing would be happening because the resistors would dissipate all the energy that the inductors might have had, and so that we would have no current, right? But at this point, we have some current, and again, the inductors are coils. They don't like change. They're going to hold the current up. Try to hold the current up slowly, right? So we're going to let it decay slowly. So we're going to have now this equation. All right. So I guess we can say this is with the source, and this is with no source. I think this is when the source these are all transient kind of things. When the source gets just closed in, we see this. When the source gets just taken out, we see this. All right, so we're going to use I of t is just the same I max, E over R, V over R, e to negative t over tau. Right? It's the same circuit, so it's got the same tau, so it's still 0.0714, or when we take 1 over tau, because it's t over tau, we get 14. All right, so, and the maximum current is still the same, 1.29 e to the negative 14t now. What happened here? Okay, that was... we lost something. 1.29, 1 minus e to the negative 14t. All right. Sorry about that. Amps. So this one, I don't know what happened to me there. We lost that. But now here, this one is the one that really has the decaying exponential. Okay. Continue on. And that's all that part B asked for, I guess. Okay. And then for part C, what is V3 as a function of time? So V3, I said, is just the inductor across the 0.3 Henry, the voltage across the 0.3 Henry inductor. And so V is, in general, V is L di dt. So V3 of t is L di dt, which in this case is 0.3 Henries times the derivative of, which one do we want to do? I guess we'll just do the last one, where this one is our I of t. It's not very specific, but we'll just assume this is for case B. And so d by dt of 1.29 e to the negative 14t. How do we take a derivative of an exponential? You just multiply by the coefficient of t in the exponent, and then it's just the same thing back again, right? So we're going to have 0.3 times 1.29 times negative 14 e to the negative 14t. Oh, boy. All right, 0.3 times 1.29 times 14, 5.42. So V3, I'll just go over here. It's a mess, but V3 equals negative 5.42 e to the negative 14t volts now. All right, just going back to our defining equation for inductors in circuits. V is L di dt. And we're using only the inductance of this inductor because we want the voltage only of that one. So we couldn't use the little baby circuit. We're going back to the full circuit. Okay, I think that's all of those parts. Let's see if we can get this one done. Part D, talking about a new circuit. What is a circuit going on here? So we have 2 capacitors and 2 inductors. All right, and we want to find the charge as a function of time. We want to know the phase angle. So we're gonna assume, do we have a given, oh yeah, we have a given voltage here on the capacitors, and so I think we can find everything. Hopefully I put enough information there. So we've got a circuit here. This is an LC circuit, and these are assumed to be ideal elements, ideal things, and so they don't have any resistance, so they don't have any losses, so they don't have any loss of energy. So if the capacitors are charged up when we start, then we close the switch, so they're going to have some energy stored in them, and we'll assume the inductors don't have any energy stored in them. And then when we close the switch, capacitors are going to give energy to the inductors, but then the inductors are going to pass it back again. And so we saw, again, we could go through the derivations. Hopefully you've seen them in the book and seen them in the theory videos, and get equations for the current, the voltage, the charge, everything is going to, and the energy is going to be oscillating. Well, the energy is going to be total constant, but it's going to be going from one place to the other. And so that's where we get into this set of equations on our equation sheet. This is for an LC circuit, and this bottom one is, and this also is for the LC circuit. And this bottom one is for an RLC circuit, where we're actually going to have some resistance. And so just looking at what happens, so when we have the circuit, do the differential equation, solve it, we get sine wave kind of things, and maybe we should put omega naught on this for now, because we're talking about just the LC circuit. And so the charge will be an oscillating circuit, or an oscillating signal. And then what is current? Current is derivative of charge. So you take the derivative of the charge, you get a current. It's also going to be a sine wave, sinusoidal oscillating signal. And in the just pure LC case, they're just sine waves. They just continue on forever, theoretically, right? When we add in a resistor, R, L, and C, now we get an exponential kind of thing like we had for the inductor and resistor circuit. And so we have a decaying cosine. So instead of just being a cosine that goes on forever, it's a cosine that is multiplied by an exponential with a negative coefficient. So it's going to come down, and eventually it's going to die out. A damped oscillation, we would call it, okay? Because the resistor is sucking the energy out. Each time it passes through the resistor, it takes some energy out from what the capacitor and the inductor are passing back and forth. Okay, but back to our circuit, we have just a nice ideal an LC circuit. But let's go ahead and make it into an even more ideal, where there's only 2 elements, one L and one C, and that's because that's what the equations are for. And again, we'll have this T equals 0, and we have at V at 0, V of 0 is 9 volts on the capacitor. Okay, so what are these capacitance values and inductance values? Capacitors, how are these connected? How's everything connected? They're all in parallel. Hopefully you can see that. So these two capacitors, when we add them together, C is going to be C total. How do we combine capacitors in parallel? That's the easy one for capacitors. They just add up, C1 plus C2. All right, so we've got 2 microfarads plus 3 microfarads. So C is 5 microfarads, okay, for our equivalent circuit here. And then inductors, L is going to be L total. But inductors, again, these are in parallel. Tops are touching tops, bottoms are touching bottoms. And so they are like resistors, so they have to be added as 1 over L1 plus 1 over L2. Luckily, nicely, me being lazy, I made both the inductors the same size, so when you have both things the same size in this equation, we just get the answer being a half, so it's 0.05 henries would be the inductance, the total inductance. Plug it in your calculator if you don't believe me. Okay, and so we've got our parameters for our circuit here. Let's get our, what we're looking for. Looking for Q of T. Okay, Q of T is we're not looking for Q of T yet. I'm on the wrong. We need Q total. Let's go up. I missed the line. So Q total, which is basically the charge on both of these capacitors. So it's the charge on this equivalent capacitor is what? At initial condition. So at the initial condition where the 9 volts is on the capacitor, what is the charge? And so it's just going to be our old friend QVC, where this is V naught and this is C total, or just the C here. And so it's going to be 9 volts times our capacitance, which is 5 micro, 5 times 10 to the negative 6 farads. So our total charge is going to be 45 microcoulombs. Is Q total naught, or just Q naught, basically, in the other equation. I think we call it the Q naught in our equation, but let's keep going here. Omega naught. What is omega naught? What is omega? Omega is our angular frequency. So omega is our rotational speed kind of thing, but in our cosine circuits, it's the angular frequency, 2 pi f kind of a thing. But we have an equation for this. So for an LC circuit, just a simple L and C with nothing else in it, we call the natural frequency omega naught is 1 over the square root of LC. All right, and so omega naught is 1 over the square root of LC. So 1 divided by square root of L was 0.05 henries, and C was 5 microfarads. So 1 divided by square root of 0.05 times, they're both 5, yes, okay, 5 to the negative 6. So omega naught is 2,000 watts. Radian, or angular frequency, or sometimes I call it radian frequency, is radians per second. Omega naught. If everything else was in the correct units, which we have henries and farads, so we are good. And then I naught. What is the initial current? Okay, so I naught, let's look at our equation here. I didn't give us a equation on the equation sheet for it, but notice that the voltage and the charge and the current are in phase with each other. They have the same angle, and I think I'm calling it beta here, and on the example problem I'm calling it phi, but it's whatever, the angle, the starting angle. And so I naught is just the coefficient of the sine wave, sinusoid, in the I equation. So in this case, I naught, which is the maximum value of current, is really what it's asking for. I max is equal to omega Q max. Omega naught, since we are operating at our natural frequency here, there's no source in there, and so we just get 2,000 times radians per second, times Q max, which is, we just calculated Q naught, Q max, same thing in this case, 45 times 10 to the negative 6 coulombs. And so we get the current then is, radians are kind of a unitless thing, and we get coulombs per second, which charge is, current is how much charge per second goes past. So units are looking good. So 2,000 times 45 e negative 6.090 amps. All right, now we can, sorry about that. We can plug into our equations here to get our current as a function, our charge as a function of time, current as a function of time, almost. Okay, so we don't have our beta, which is, let's call it beta here. And so we need to get our beta so that we can find everything as numerically. So Q of t, let's just write it out here so I don't have to keep going back and forth. Is Q peak cosine omega naught t plus some phase shift. All right. And so how do we know this phase shift? How can we figure out? We need to know some sort of initial conditions, what's happening when we close the switch, so we can have a t equals 0 point, so we can know, basically that determines where we start in our cosine wave, right? Because Q peak is just Q max. I call them 3 different things, but anyway, it's the coefficient of the cosine in the oscillation equation. And so how can we get beta? Oh, let's see. So we know Q peak. Well, we know the Q peak happens at the initial point. May be easier to look at it in terms of current. So the current equation is I of t is negative omega Q peak sine omega naught t plus beta. And when we close in the switch, again, the inductor doesn't like change, so it's not going to let the current go boom right automatically. So the current is still going to be 0 at the instant after we close the switch. And so we can say I of 0 equals negative omega Q peak. And then if we put in 0 here, we get sine of 0 plus beta, so sine of beta. And so beta is going to be 0. Yeah, okay, beta is 0. Which makes sense because sine starts at 0, the current starts at 0. Yeah. Okay, we're all good. And so beta is 0, and so Q of t then is Q max, Q peak, Q0, whatever we're calling it, 45 microcoulombs. We're going to just put microcoulombs for the units out here. 45 cosine of omega 2000 t plus beta, which is 0. All right, so there's Q of t. Okay, and then for I of t is the next thing. So that was part E, and part F, I of t. Again, we, I think, have everything, all the pieces just plugging in numbers. So we got negative, omega is omega naught in this case, and so omega naught is 2000, negative 2000 times Q max, 45 times 10 to the negative 6 coulombs, radians per second. Cosine, not cosine, This one is sine because we took a derivative. Sine of omega t 2000 t plus beta, which is 0, and then this will be amps when we get it multiplied out here. But then we already calculated the I max, yeah, right there. So I of t is 0.090 sine of 2000 t amps. And of course there's one more. All right, we'll try to do G over here so we don't lose everything here. Scooch over our calculator. Okay, so for part G it says now we're going to add a resistor in here. All right, adding a resistor. Let's make it red so we can see something changed here. Adding a resistor, like I said, causes losses, causes the energy to go away. So we don't have this current that goes on forever as a sine wave, right? With a nice fast frequency. We are going to have the sine wave at the start, but then it's going to get smaller and smaller and smaller as it goes. All right. And so what is it asking for? What is Q of t if we add a 1 ohm resistor? Okay, so we're still going to have the same stuff at the beginning, right? At the very instant it closes. No energy has been lost yet, so we're going to still have our Q peak, Q naught, Q whatever is still going to be 45 microcoulombs, and our I max, I peak is still going to be the 0.090 amps. But as we go, we're going to have that exponential in there. So our Q of t is going to be, using this equation now, we have Q peak the same, beta is the same, gone, but we have this exponential term in here that's going to multiply the cosine so that it's going to make it shrink, and we have a new frequency, right? So omega prime is our old frequency, but now the resistor causes a change in the frequency as well. All right, so let's get omega prime. Let's get omega prime first. Omega prime is square root of 1 over LC minus R over 2L squared. And so just plug it in since I don't have room. So we're going to have square root of 1 divided by, in parentheses, LC. Well, I guess I don't have that without the square root. So L is 0.05 and C is 5e negative 6. Close those parentheses. We've got 1 over LC, and then we're going to subtract from that, in parentheses, R, which is just 1, divided by 2 times L, 0.05. Close those parentheses, close these bigger parentheses, and square that. Let's see if, oh, it doesn't like it. What did I do wrong? There's a little something at the front. I don't know what that was, but let's try this. Okay, so we got 1 over LC, square root 1 over LC minus 1 over R over 2L. Good. All right. Okay. I made my resistor too small. So omega prime, let's change that to make R equal to something bigger. Where'd it go? So let's say R is 1 k ohm, just to see an effect, because again, I've got 1.999975 as opposed to 2000. Okay. So let's do that again, where let's make R 1000 instead of just 1. Come on. Okay, so that just changes That's the only place R shows up, so I'm going to make that into 1,000 instead of 1. Oh, now what? Okay, we can't do 1,000 because that makes this a non-real result. 1,000 is too big. I should have done this before, so let's make it 100. Let's see if 100 works. Okay, he likes 100. We'll go with R is 100 instead. Where is that? Okay, so if we put in R equals 100 ohms, we get 1732 for omega prime. Radians per second. Okay, and we also need, looking in here, it's a little bit hard to see maybe, but the coefficient of t in this exponential is r over 2l, like 1 over this. So let's calculate r over 2l just for no, it is that r over 2l. Yes, okay. So it's not 1 over that, it's just that. So we've got r was 100 now divided by 2 times 0.05. So that is 1,000. Okay. So the coefficient of t in the exponential is 1,000. So now we've got q of t is q peak 45. And the whole answer is going to be microcoulombs. And then q peak e to the negative r over 2l e to the times t e to the negative 1,000 t times cosine omega prime 1732 t plus beta, which is still 0 because the current is still 0 at the beginning. Okay, and that is microcoulombs. Okay, omega prime, got the exponential, got our new q. All right, and that is it. So we'll go ahead and stop there.